I'm going to discuss about the phasor relationship of R, L, and C. But before that, it is very important that we learn something through the previous discussion for us to be able to comprehend this topic. So now, we're now able to transform phasors from each three forms to one another, from polar, something. And now, let's proceed to its simplification by establishing its relationship between phasor voltage and phasor current. So the simplest case is the resistor. Now, let's take a look at this diagram. This is diagram A and diagram B. Diagram A is called the time domain. And diagram B is called frequency domain. So, defining the equation of the time domain, we have T is equal to R I T. Now, let's apply complex voltage. So, defining the equation in the time domain, we have Vt is equal to RIT. Now, let's apply complex voltage and having its complex current. So we have this one. Now, we have the exponential form of the voltage and its trigonometric form. Trigonometric form of the current and its exponential form. Now, using this equation, let's apply this one and this one to this equation. Now, we have obtained this one. V maximum Ej omega t plus theta is equal to R times I maximum Ej omega t plus phi. Now, suppressing both sides by dividing j omega t, we get this equation. V maximum E j theta is equal to R times I maximum j phi. Or in polar form, we have this one. V maximum angle theta is equal to R times I maximum angle phi. Now, let's remember V maximum angle theta and I maximum angle phi represents the general voltage and current phasors of V and I. Thus, we have V is equal to R times I. So, now we have the current voltage relationship. In phasor form for resistance, it has the same form as the relationship between time domain voltage and current. And the equality of theta and phi is apparent, which means it is seen to be true. Now, to fully understand this thing underlined here, let's have an example. So now, let's have an example that uses both time domain and frequency domain. Now, we have a voltage of 8 cosine 100t minus 50 degrees across a 4 ohm resistor. Now, first, we have the time domain, which we had V t is equal to R I t. Okay, we're looking for its current. So we have I t is equal to V t over R equal to 8 cosine 100t minus 50 degrees all over 4. Having an answer of 2 cosine 100t minus 50 degrees. Now, let's have the frequency domain. Frequency domain having formula of V is equal to Ri. Now, again, we're looking for its current. So I is equal to V over R. Now let's remember, this one right here is a trigonometric. Am I right? So this one can be transformed into polar form. So the polar form of this voltage can be written as 8 angle negative 50 degrees. So let's apply this one. Let's apply the given into this equation. So we have I is equal to 8 angle negative 50 degrees over 4. Now, we have a current of 2 angle negative 50 degrees ampere. Now, we have arrived to this answer. We have 2 cosine 100t minus 50 degrees ampere for the time domain. Then we have 2 angle negative 50 degrees ampere for the frequency domain. Now, even if we transform this answer from the frequency domain into the time domain, it is still evident that the same expression will be obtained for the current. So now let's proceed to the inductors. So in this figure, figure A is the time domain. And figure B is the frequency domain. Defining the equation of time domain, we have V is equal to L di over dt. Now, let's apply a complex voltage into this equation. Complex voltage and complex current. We have V maximum Ej omega t plus theta is equal to L derivative of I maximum Ej omega t plus phi over d. So, taking its derivative, we had V maximum Ej wt plus theta is equal to J omega L I maximum Ej omega t plus phi. So suppressing both sides, dividing it by J omega t, we have V m E J theta is equal to J omega L times I maximum E J theta. Now, applying same concept, during the resistance, eliminating this one and this one, we can now have V is equal to J omega L times I. So let's have an example. So 8 angle negative 50 degrees volt is applied at a frequency W is equal to 100 rad per second to a 4 Henry inductor. Look for its phasor current. So first, we're going to solve this problem. So take note of the given. We have 8 angle negative 50 degrees volts. We have a frequency of 100 rad per second, then a 4 Henry inductor. Now we have the formula. We have the formula V is equal to J omega L I. So we're looking for its current. We'll have I is equal to V over J omega L. So now let's substitute this given for equation A. Given to this equation. We have I is equal to 8 angle negative 50 degrees over J 100 times 4. Since these two given is not in the same form, let's transform this one into a polar form. Now we'll have 8 angle negative 50 degrees, and now this one will have 400 angle 90 degrees. Now solving, we have 8 over 400 angle negative 50 degrees minus 90 degrees. Now we'll have 0.02 angle negative 140 degrees. So now we have the final element to be considered, which is the capacitor. Now we have these two diagrams, A and B. A is the usual time domain, and we have B, the frequency domain. Start. So having its time domain expression of IT is equal to C times dVt over dt. Now we have to again have its current and voltage to its complex quantities. We have Im Vj t plus P is equal to C derivative of V M P J plus theta dt. Taking its derivative, we'll have Lm P J omega t plus V is equal to J omega C times V maximum J omega t plus theta. Again, we suppress both terms. We suppress J omega t. we'll have E J V is equal to J omega C V maximum E J theta. And now, recognizing its voltage, phasor voltage and phasor current, will have I is equal to J omega C V. So to fully understand those definitions, we'll have an example. If the phasor voltage of 8 angle negative 50 degrees volts is applied to a 4 farad capacitor at a frequency of 100 rad per second, find the phasor current. So first we'll take down the given. We have 8 angle negative 50 degrees volts. We have 100 rad per second. Then 4 farad. Now we have the equation I is equal to J omega C times V. Now let's substitute the given to the equation. We'll have 8 angle negative 50 degrees times 100 times 4. So now we'll obtain the value of 3200 angle negative 50 degrees. We have a very huge value here because assuming the value of the capacitor is way too unrealistic. Now let's have a recap in our discussion. So we have discussed that these three passive elements have its relationship: resistor, inductor, and capacitor. And each of these passive elements have its expressions in time domain and in frequency domain. We have its equation of V is equal to Ri in frequency domain, and V small letter v is equal to R times small letter I in time domain. Also in this inductor and capacitor, we have also had these equations. Now, each expression is algebraic in nature as we have these equations, and all of them are linear.